Today our topic is viscosity and drag force. These are fundamental concepts and terms used in fluid dynamics. So let's see what is fluid dynamics. Study of fluids in motion is called fluid dynamics, and the examples of these phenomena include blood flow, rain falling, and water flowing in rivers. Such a phenomena is shown in figure. We can see a dam in this figure and the water is spilling out from this dam. This water in motion represents an ideal case of fluid dynamics. So now we will define viscosity. Frictional effect between different layers of fluid is called viscosity. The viscosity of a fluid depends upon the strength of intermolecular forces, and different fluids have different viscosities. Here in diagram we can see two fluids, the one is honey and the other is water. We know if we start filling these jars with water and honey, we will see the jar with water will be filled more quickly as compared to jar with the honey. So this means honey has greater viscosity compared to water because it finds it difficult to flow when we compare it to the water. The next thing we will understand is the drag force. When an object moves through a fluid, it experiences a resistive or retarding force which is called drag force. For example, if you are traveling in a car and you take your hand out from a running car, you will feel air exerting force on your hand. Here in the diagram, a case in which drag force acts on a bicycle rider is shown. You all must have experienced that when you are riding a bicycle, the air offers you resistance. It opposes your movement as you move. As your speed increases, the drag force exerted by air also increases. So we can say this drag force has some dependence upon the speed of moving object. Stokes law. This is a fundamental law in fluid dynamics which tells us about the drag force acting on an object moving through a fluid. So for a spherical object of radius r which is moving with velocity v in a fluid with viscosity coefficient eta, drag for acting on object is, the drag force is given by F is equal to 6 pi eta rv. This equation represents the Stokes law. Here in the diagram we can see a droplet or an object of mass m is falling through a fluid. This object falls under the action of gravitational pull. While this object moves downward, a viscous drag due to fluid acts upward, and the acceleration of this object is due to net force, which can be found by the difference of gravitational pull and viscous drag. As this object gains speeds, viscous drag also increases. Today our topic of discussion is terminal velocity. So first of all, we will define what is terminal velocity. Constant velocity attained by an object when drag force becomes equal to applied force. Consider a body is moving through a viscous medium. We know when an object moves through a medium, a drag force is exerted upon that object. When the drag force and applied force becomes equal and objects start to move with a constant velocity, we call this velocity terminal velocity. Examples include the terminal velocity attained by rain droplet while falling under the action of gravity, and a similar example is of fog droplet. The fog droplet, often seen as a stationary or very slowly falling object in the air, it falls with a constant velocity due to drag force being equal to gravitational force. And thus we say fog droplet moves with a terminal velocity. So let's calculate the terminal velocity of this fog droplet. Consider a water droplet in fog is falling under the action of gravity, that is, its weight mg is pulling this fog droplet downward. As it moves down, it gains velocity due to gravitational acceleration. As velocity increases, by Stokes' law, drag force also increases. Net force acting on this droplet will be weight and drag force. When we find the difference of these two forces, we will get net force. Weight is downward, drag force is upward. So net force is equal to weight minus drag force. A stage comes when drag force acting on the droplet becomes equal to its weight. At this stage, net force acting on the droplet becomes 0. So net force is equal to 0, and thus 0 is equal to weight minus drag force. We will rearrange this equation and it becomes weight is equal to drag force. Simply inserts the value weight is equal to mg, we already know it. Drag force is given by Stokes' law, which states the drag force will be equal to 6 pi eta rv. If you don't know about Stokes' law or drag force, kindly visit the other tutorial given in the link. So we rearrange this equation and the terminal velocity becomes Vt is equal to mg divided by 6 pi eta r. We just isolated Vt here. Now we will find the value of mass and volume to insert this equation. The mass of droplet is m is equal to rho v, where m represents the mass, rho represents the density, mass density, and v represents the volume. We all know density is equal to mass over volume, so we rearrange and get the value of mass, which is equal to rho v. And as we all know that the water droplets are in spherical form, so the volume here used will be of a sphere, which is equal to 4 by 3 pi r cube. So we use this volume in the mass formula, which is rho v, and thus the mass becomes 4 by 3 pi r cube multiplied by rho. V is replaced by 4 by 3 pi r cube. Now we will insert this value of mass in above equation, which will give us the value of terminal velocity, and after simplification we will get 2g r square rho over 9 eta. This is the relation which will give us the terminal velocity of a droplet or a fog droplet falling under the action of weight or gravitational field in air.